It's a dream come true. You've been thinking about this for 20 years, and now you finally see it, and it looks like in your dreams.
For decades, the mysteries of black holes have captivated the scientific community and the public alike. These enigmatic objects, with gravitational fields so intense that not even light can escape, have long been thought of as one-way portals, cosmic cul-de-sacs where matter enters but never returns. The very idea that anything could emerge from a black hole has traditionally contradicted the core principles of physics. Yet recent observations from the James Webb Space Telescope, JWST, have begun to unravel this seemingly immutable truth. In one of its most breathtaking discoveries to date, JWST has captured high-resolution evidence of something actively being ejected from the vicinity of a black hole, and the implications are nothing short of revolutionary. Before we start, hit the like and subscribe buttons for more exclusive news. The event in question occurred in a distant galaxy billions of light-years from Earth. While black holes are often surrounded by turbulent environments marked by jets and accretion disks, this particular observation revealed a structured outflow that appeared to originate not just near the event horizon, but from a region previously thought to be entirely inaccessible. This wasn't a chaotic burst of high-energy radiation, or an enormous jet streaming perpendicular to the black hole's disk, as has been seen many times before. This was something far more coherent and strangely deliberate in its structure, as if the black hole itself was releasing information or matter that had previously been swallowed. What JWST observed was a distinct plume of energetic particles, narrow in shape and clearly delineated from the surrounding electromagnetic noise. The outflow, spanning light years in length, exhibited a curvature in its trajectory, suggesting that it had been influenced by extreme gravitational forces before being launched outward. What made this phenomenon particularly compelling was the spectral signature captured in the infrared, Webb's specialty. It revealed atomic and subatomic particles arranged in unusual patterns, hinting at a level of complexity that has baffled scientists across disciplines. Initial analysis ruled out a standard relativistic jet as the source. While jets are indeed launched from regions near the poles of spinning black holes, they usually stem from the magnetic interactions in the accretion disk and not the black hole itself. This plume, however, did not conform to the expected properties of such phenomena. Its spectrum bore traces of material that seemed too deep, too close to the black hole's core to have been expelled by ordinary processes. There were signs of heavy elements that would normally only be found in high-density stellar interiors or extreme gravitational environments. This pointed to a new, previously unseen mechanism of ejection, perhaps rooted in the quantum nature of space-time itself. The implications are vast. For one, this challenges the traditional conception of black holes as absolute endpoints. If something can escape, or at least be processed, and then emitted, from within a black hole's grip, then the fundamental laws of physics, particularly the interplay between general relativity and quantum mechanics, require urgent re-examination. It opens a window into the most extreme conditions in the universe, where our current models fall apart. The observation lends unexpected credence to certain theoretical frameworks that have long existed on the fringes of mainstream science, including ideas like Hawking radiation having macroscopic expressions, or the notion that black holes could serve as bridges to other parts of space-time. This event does not imply that matter is escaping the singularity directly, a concept still considered implausible by most theoretical physicists. Instead, it suggests that processes occurring just outside the event horizon might be far more complex than previously understood. It is possible that quantum tunneling or some other exotic phenomenon could be allowing matter and energy to escape in highly organized ways. Another possibility is that the black hole is not truly a one-way destination, but rather a kind of cosmic transformer, one that absorbs, compresses, and eventually reconfigures matter and energy before releasing them in a new form. The observational capabilities of JWST played a pivotal role in this discovery. Its unparalleled infrared sensitivity enabled it to see through the dense veils of interstellar dust that obscure most of the universe's invisible wavelengths. Where other telescopes might have seen a blur or been blinded by radiation, Webb was able to resolve the structure of the plume with clarity, capturing a sequence of images that demonstrated its consistency and directionality over time. These observations were corroborated by data from other observatories, including X-ray telescopes and radio arrays, which confirmed that the phenomenon wasn't an observational artifact but a real persistent event. Perhaps most intriguing of all is what this could mean for the information paradox, the long-standing puzzle about what happens to information that falls into a black hole. If black holes can emit matter in a way that carries information about what they previously consumed, even indirectly, this would represent a monumental shift in our understanding of entropy, causality, and the arrow of time. It would suggest that black holes are not destroyers of information, but custodians capable of re-encoding and releasing data in ways we are only beginning to comprehend. In essence, this discovery edges us closer to the long-sought goal of unifying general relativity and quantum mechanics, the dream of a theory of everything. Black holes, once thought to be the ultimate enforcers of cosmic silence, may instead be the universe's most eloquent storytellers, whispering secrets encoded in the very fabric of space and time. The ejection captured by JWST might represent the universe's version of a message in a bottle, a relic from the far side of gravity's absolute dominion. While further analysis is needed and countless questions remain, this finding marks a turning point in black hole research. It validates the notion that our understanding of gravity, quantum fields, and high-energy astrophysics is still in its adolescence. As JWST continues its mission, more such phenomena may come to light, offering not just new knowledge, but entirely new questions to ask. Already, theorists are racing to model what kind of mechanisms could produce such emissions, and whether similar outflows could be harnessed to reveal deeper truths about the nature of dark matter, dark energy, or even the origins of the universe itself. This event also redefines what it means to see a black hole. Traditionally, black holes have been known only by their shadows, regions of absence surrounded by blazing rings of radiation. But with JWST's clarity, we are now glimpsing behaviors that suggest presence and activity, not mere void. These emissions are not just after effects, they are manifestations of processes occurring at the very edge of known physics. They are signs that black holes might be interactive objects, participants in the cosmic dance, not just spectators or endpoints. Beyond the theoretical ramifications, this discovery has philosophical dimensions as well. Humanity has always sought the boundaries, the edge of the map, the end of the ocean, the final frontier. Black holes have long represented the most final of all boundaries. The notion that something can come out of one is as psychologically profound as it is scientifically staggering. It changes our relationship with the universe, suggesting that even the most extreme and irreversible processes might, under the right circumstances, contain the seeds of return, of renewal. This revelation also forces a reconsideration of how we interpret other energetic phenomena in the universe. Could some of the cosmic rays bombarding Earth, some of the high-energy particles with mysterious origins, be linked to similar black hole ejections? Could phenomena we currently attribute to other astrophysical events, like gamma-ray bursts or magnetar flares, have at least partial origins in these newly discovered emissions? The door is now open for re-examination of past data with fresh eyes and updated models. Importantly, this discovery acts as a call to action for the scientific community. It underscores the need for continued investment in high-resolution multispectral telescopes both in space and on Earth. As technology advances, so too does our capacity to answer these fundamental questions. The JWST's capture of this black hole outflow is a milestone not just in astronomy, but in the broader pursuit of understanding reality at its deepest level. It represents a nexus point, the meeting of empirical observation and speculative theory, of cutting-edge engineering and age-old curiosity. Moreover, the event highlights how much of the universe remains unexplored and how tools like the JWST are finally giving us access to these distant and difficult-to-reach regions. While we've mapped much of the observable universe in terms of stars and galaxies, we are only now beginning to unravel the behaviors of its most extreme and mysterious components. The black hole outflow captured here is not just an isolated curiosity, but part of a broader tapestry of cosmic behavior that is only now coming into focus. If you liked this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on James Webb's discovery? What do you think is emerging? We want to hear from you. Thank you for watching, and see you next time.